Hello and welcome to the Astro Podcast. Today we are thrilled to be welcomed by Anirudh Chiti, a Brinson Prize Fellow at the University of Chicago. He will also be leading a large imaging program with a newly installed imaging filter on the dark energy camera. His work surrounds galactic archaeology, chemical evolution of the early universe, and the role of dark matter in dwarf galaxies. Welcome, Anirudh. And is there anything you would like to say before we start this podcast?
No, thank you for having me and very excited to be here.
Great. Well, it's amazing. And today we'll be diving into this new topic that I've recently known about, which is called galactic archaeology. And just like the name suggests, it's kind of like when we find fossils of dinosaurs from millions of years ago, and we understand its structure and how they used to behave back then. The same goes for galactic archaeology, where we look at the old remnants of galaxies and we can understand how they were formed when they merged with other galaxies and how they've evolved over these billions of years. So, my first question is, can you please give us a small perspective of, galactic archaeology and what new findings have you guys uncovered from it?
Yeah, so broadly speaking, galactic archaeology is just the investigation of ancient components of our own galaxy and nearby galaxies to understand what they might have looked like in the early universe. And so there are some pretty fundamental aspects of this that are useful. The first thing is that if you look at a star and you observe a star in the night sky, and you take a spectrum of the star and understand its composition based on that, what you're actually looking at is what the star was composed of when it first formed in the universe. And that's because the outer layers of stars don't change much over the course of their lives. So if you find a star that formed 13 billion years ago that still exists in the Milky Way today, you can study it in detail to understand what the chemistry of the very early universe might have looked like and what the very early Milky Way might have looked like. And you can do studies of these stars to trace what elements were produced in the early universe going until the present day. You can also do things like study the motions of these stars, their kinematics, their velocities, to trace the evolution of the Milky Way, to see how the Milky Way's disk, the spiral arms, formed over time. And you could even trace individual galaxies that are surrounding our own ones that formed in the early universe to see what conditions of under which those galaxies formed were. So it's kind of like you can look nearby, you can find these fossils from the early universe, and you can understand its properties. And it's very analogous to when something like Hubble or JWST looks really far back in time, looks really far away, and then studies the early universe from that perspective too. So you can kind of bridge, our understanding from that regime to what we can learn about the early Milky Way and galaxies surrounding it. It's kind of like you said, looking at fossils, and the other approach is like Jurassic Park, where you actually see the dinosaurs in real time.
So, is there any like big discovery that you guys have
Oh,
made from looking into galactic archaeology?
yeah. So the nice thing about the fact that we're looking at these things that are nearby is that we can study them in really great detail that you can't with JWST or HST. So one thing that we've discovered over time is that for whatever reason, a lot of the oldest stars in the universe that are enriched by just the first supernovae seem to have a lot of carbon in them. So whatever was producing heavy elements in the early universe, whatever types of supernovae the very first stars were going off in, seem to have been overproducing carbon relative to other elements. This is a pretty interesting discovery, right? That carbon might have been ubiquitous. And now recently with JWST, with the direct observations, people are finding that there's a lot of nitrogen in the early universe. So you're kind of building up this picture of what the periodic table might have looked like at very early times, which is cool. Another discovery that's really neat is that now with these really big missions, we have data on a bunch of stars in the sky in our own galaxy. So we have motions in the sky for about 1 billion stars with the new Gaia mission. Well, it's not new anymore, but it's called the Gaia Space Mission to measure the motions of stars. And from this, we can kinematically reconstruct what kind of events might have shaped the early Milky Way as it was forming. And so, for instance, we know now that the last major galaxy merger with our own galaxy happened about 9 to 10 billion years ago with something that was known as the Gaia sausage Enceladus. It's a very strange name, but but because of the motions of stars, we can reconstruct this and and see that this must have happened. So we can uncover key moments in our own galaxy's evolution to understand the story of how, our own system formed.
So is there any, insight that you guys have made about our own galaxy, just as you said? Like specifically our Milky Way galaxy, is there anything new that we've discovered about how our galaxy was formed or where it may have came from?
Yeah, yeah. So people are reconstructing the full history. It's called the merger history of our galaxy. So galaxies form in the universe by through the merging of smaller systems. So that's how galaxies form. Is you have small galaxies that form first, they start merging together to form larger galaxies. Then over time you end up with systems like the Milky Way. And this process will continue over time. So the Andromeda galaxy is on a collision course with us. It'll merge with our galaxy and form an even bigger one. And what we can do now that we have all of this data is in this approach of galactic archaeology, researchers can reconstruct what the full merger history of the Milky Way might have been like all of the galaxies that merged together to build it up, or at least all the major ones. And so there's been a lot of progress in picking up and identifying these building blocks of our own galaxy to get a full understanding of how it might have formed. Um, and in addition to that, people are connecting this to different theories of how we think galaxies might have formed as well, right? So different simulations of galaxy formation predict different kinds of outcomes of this kind of process. So it's interesting from that perspective. In addition to this, people have been doing some work on how different components of our galaxy form. So, for instance, people can now use this data to trace when the disk of our galaxy formed. So, when I say disk, the Milky Way has spiral arms. So, people can often ask, like, when do spiral arms emerge in the Milky Way, right? Like, when do these things form in the process of a galaxy forming? So, we can use these massive data sets to trace, at what metallicity or age you start seeing the spin up of the arms to trace when that formed. And so that's kind of cool. And we can extend this to other systems too and learn how galaxies form.
And like as you said, going into our next topic, where you said that galaxies form from smaller systems, and I know that one of the situations could be from dwarf galaxy mergers can cause even bigger galaxies to form. And going into, I know that you also work a little bit on dwarf galaxies, and that was actually one of our main topics in the previous episode was Ava Poulsen, who's also Anirudh's colleague at University of Chicago. So in dwarf galaxies, I know that you mainly research more on the dark matter that's enriched in these dwarf galaxies because this allows this allows astronomers to test theories and the possible particle candidates of dark matter. Like for instance, now we have the weakly interacting massive particle WIMPs is one of the candidates. But I feel like before we get into the different candidates, I wanted to understand what is dark matter and why is it important to find it in dwarf galaxies.
Yeah, that's a really good question. What is dark matter is a question that many people are thinking about. And very broadly, all we know about it is that it is some kind of substance in the universe that appears to interact with itself and with other matter, the matter that we know about, the periodic table, through the gravitational force. And as far as we can tell, there's no other form of interaction. That's why it's called dark matter, because we don't actually know what it is. But observationally, we see signatures of this all over the universe, right? So we see the fact that galaxies seem to have much more mass than their luminous matter, than the stars seems to indicate. You might have discussed this with previous people, but there's this example of something called the bullet cluster, where we see evidence of two clumps of dark matter that seem to have passed through each other, but then the gas got trapped. And you can see gravitational distortions of light behind the dark matter. So we see evidence of this like excess matter that's interacting through gravity that has mass, but doesn't seem to be interacting in any other way. So it's kind of an enigma. And I think that's about the state of the field, is we see it, in our Milky Way, we see it in dwarf galaxies, we see it in big galaxy clusters, but we're not quite sure what it is. And the reason dwarf galaxies are interesting to study it is that they seem to have the highest dark matter to regular matter ratio of any system that we know of. So the smallest dwarf galaxies have about 1,000 times as much dark matter as matter in stars. And so, because of this, they're really interesting sort of testing grounds for what theories of dark matter could be.
And it's pretty interesting to know that the dwarf galaxies have much more dark matter. And I know that dark matter is kind of one of the reasons why galaxies spin as well, which is why we had first uncovered dark matter in galaxies. So does that mean that dwarf galaxies spin much way faster than normal galaxies?
Oh, that's a really good question. So, we don't see stars in the dwarf galaxy spinning because there are so few stars. And
Okay.
typically we see spins in galaxies that have recently formed stars or have these like spiral arms. And whereas the smallest dwarf galaxies that we know of are kind of just like blobs, they're spheroidals. So the motions of the stars is kind of random.
Right.
It's an interesting question, though. I actually don't know off the top of my head the exact cause of this.
And when how did you guys come about looking and knowing that? Because I know that dark dwarf galaxies, you guys have just received recognition. We've only been studying it for the past 30 years. And how did you guys come about finding dark matter in dwarf galaxies?
Yeah, it's a really good question. So there are different kinds of dwarf galaxies, and for the very smallest ones, those are the ones that have 1,000 times as much, hundreds to 1,000 times as much dark matter as regular matter. And these really small systems are known as ultra-faint dwarf galaxies. And the name just means they're really faint. So they only have 1,000 stars. So think about that. So the Milky Way has, billions and billions of stars. And these systems have just 1,000 stars and they're still considered galaxies. And so because of that, they were discovered only recently, the smallest dwarf galaxies. So in about 2005, they, they're younger than me. They might even be younger than you. Maybe not as young as you, actually. But so people went out and measured the velocities or the speeds of individual stars in these systems. And because these systems are so faint, so believe it or not, you can only measure the speeds of like 10 stars in each system, 10 to 15 stars. But based on that, you're able to derive something called the velocity dispersion, which is how spread out the velocities of the stars are. And then from how spread out the velocities of the stars are, you can derive the mass of the galaxy. And so even though the galaxies only had about 1,000 stars, um, the mass that was required to get the velocities of stars to spread out that much was something like 100,000 or a million. So then they were like, okay, there must be something that's causing this effect. So there must be a lot of dark matter there.
Here's the conclusion that dark matter could be the reason for this.
Yeah, at least in this case. Yeah, yeah.
So, some theories suggest that dark matter could affect the internal structure and motion of stars in these dwarf galaxies. So, maybe what's your perspective on that?
Yeah, this is also a really good question and an active area of research. So different models of dark matter predict different internal structures of it's called the gravitational potential, or how dark matter is distributed in the center of these galaxies. And so some models of dark matter predict a very steep internal potential. It's called a cusp. And some predict a shallow internal potential, like it's called a core. And if you have a cusp or a core, that will affect the motions of stars near the center of these galaxies, right? And so a lot of people are interested in dwarf galaxies and the centers of galaxies to distinguish whether you have something like a cusp or a core. Because that tells you something about the model of dark matter, and it'll also affect the motions of stars that you'll see
Right.
as well.
So,
Yeah.
I was actually going through one of your papers and I read across this title and it seemed extremely interesting to me where you guys had found a dark matter halo around an ancient dwarf galaxy. There's a lot to, unpack there. Like, what is a dark matter halo, and what do you mean by ancient dwarf galaxies, like really, really old dwarf galaxies? So my first question is, what is a dark matter halo, or what is a halo?
Yeah, so a dark matter halo is a distribution of dark matter, the distribution of dark matter that galaxies appear to be embedded in. So a dark matter halo is just the component of dark matter that is associated with the galaxy. And so our own galaxy, the Milky Way, um, the what we think of as the spiral arms are about 8 kiloparsecs in length, in radius, but the dark matter halo is about 200 kiloparsecs in radius. So even though we think about our Milky Way galaxy as this disk, the spiral arms, the actual distribution of matter that's associated with it is about 20 to 30 times as wide as that. It's just basically a blob of dark matter that you know our galaxy sits in.
So, as I was looking through your paper, you guys had specifically found a galaxy called Tucana 2. And while researching into it, you realized that the stars in these galaxies were very extremely metally poor. And it had an, as you said, as you just explained, an extended dark matter halo. And you found, and you used some mathematical tools like the NFW profile to find how, to model how dark matter is distributed along these halos. So how was it, why was this such a significant discovery for you guys?
Yeah, so this was one of those systems that's called ultra faint dwarf galaxy that I mentioned before, or some of the smallest systems that we know of. And so these galaxies are really interesting because you know how I mentioned before in the podcast that we think galaxies form from the bottom up, where small galaxies form first and then combine to form larger galaxies, and then this process continues until you get the Milky Way. So a natural outcome prediction of this is that the smallest galaxies should kind of be like the first galaxies that formed in the universe, right? Or analogous to that. And indeed, when we look at a system like Tucana 2, like a smallest dwarf galaxies, we find that all of their stars are extremely old. So what this means is that these really small systems are kind of like prototypes of galaxies that formed in the early universe. And since they're nearby, we can study them in a lot of detail. And what we managed to do is detect the first population of stars in the outer regions of one of these galaxies for the first time. So before, because these galaxies were so small and so faint, you could just find like 10 to 15 stars in their center, and then that was basically it. Like it was very hard to find to map out the outer regions. But we were able to do that in this paper. And what we thought was really surprising is, first of all, we didn't expect to make this discovery. So it was completely unexpected. And then we found these stars in the outer regions, and we found that there was nothing obvious that was pulling the galaxy apart that could give it these kinds of stars sort of this far away. And what this meant, what we took this to imply, was that there was a distribution of mass that the system was embedded in, and these galaxies were populating the outer region. And if you do some math, you find that, you can derive what the mass of the dark matter halo should be. And it was exciting because it was actually the first direct observational evidence that these small scale galaxies that formed in the early universe might have existed within their own extended distribution of dark matter. So, you know how I mentioned in the Milky Way, we see, you know, a dark matter halo that's much more extended than the stars, most of the stars that we see in it. Um, and based on models of galaxy formation today, this should actually exist for all galaxies. We see this evidence in other massive galaxies. We see evidence for this in smaller galaxies, but this was the first time that there was evidence for this in, that very small, 1,000 star galaxy regime that might have, resembled what early galaxies in the universe looked like. So it was just a nice sort of way to tie up this picture.
How common are these halos in dwarf galaxies?
Yeah. It's a good question. Observationally, this is, I think, still the most compelling one. It's very hard to find these. But a prediction from the modeling is that they either should exist around most or all of these, or they've been pulled apart by the Milky Way, by our own bigger galaxy, because they're orbiting it, in which case they wouldn't have it.
So one more a question I had on dark matter was that we obviously don't know much about dark matter as yet because we haven't even found what it's made of. But I think, as you said, that these dwarf galaxies contain, well, some dwarf galaxies, they contain a lot of dark matter, like 1,000 times more. So do you think looking more into dark matter, into dwarf galaxies, can help us know or understand more about what they're made of and find new candidates for it?
For dark matter.
Yeah, for
Uh,
dark.
yeah, yeah, I think so, and especially um, not beyond measuring the specific distribution of dark matter within these systems, just getting a handle on how many of these systems exist around our galaxy, how small these systems can get, is actually a really powerful probe of what dark matter might be. So different models of dark matter predict different distributions of these small galaxies depending on how much structure you get on small scales from the dark matter model that you have. And in particular, some models of dark matter where the dark matter interacts with itself predict that you actually shouldn't form galaxies below a certain mass. So if dark matter interacts with itself in a certain way on small enough scales, you actually wouldn't end up with galaxies below, let's say 100 stars or 10 stars. So knowing how small a galaxy can be, or how small galaxies, uh, knowing the smallest galaxy that can exist, actually tells you something about what dark matter might be and how it interacts with itself. Um, yeah, I mean, I think a very good question would be, well, you find 1,000 times as much mass in one of these as stars. What if it's just a giant black hole, right? Like, what if that's just what dark matter is? Um, but the thing is, we know that because there's only 1,000 stars, you actually don't have enough stars to make a black hole that big. So you can start to rule out things in interesting regimes like that too.
That's pretty good insight. And we know that as our universe is expanding, galaxies are getting further and further away from each other. And as our universe starts expanding and all these dwarf galaxies start merging with each other, do you think in the near, billions of years, do you think we'll still have dwarf galaxies around, or will it all just be one big galaxy, which is all just merged together?
Yeah, that's a really really good question, and I think there's two interesting points to this, right? The first is, as you might know, the universe is accelerating in its expansion based on dark energy, and one prediction of this is that if you go forward, I think like 10 or 20 billion years, uh, the only galaxy that we will be able to see will be the Milky Way Andromeda merger. And then if you go forward, I don't know the exact time scale, but 50 billion years, yeah, it'll just basically be one blob. So we will just have an island universe of our galaxy, and then all the other galaxies will be mixed up,
The
and that's
universe will be
what we
pretty
share.
dark because everything is just going to move away from each other and everything will become isolated. So that'll be pretty interesting to see in the near future. Obviously, we won't be there that long. But so going into a little bit about observational evidence and the missions that have been um, specifically targeted towards finding dwarf galaxies and knowing more about them. Because with new advancements of imaging, like the one that you're leading, the dark energy camera, astronomers are detecting much fainter and more distant structures of galaxies than we've ever been before. Like you said, the ultra faint galaxies. So, with your work, I want to know a little bit about, the dark energy camera and what it's doing and your work that you'll be doing for the dark energy camera. So if you can give a brief explanation.
Yeah. So the dark energy camera was an instrument that was built about a decade ago. Now, I wasn't involved in the building of it, but I'm very privileged to be able to use it for the science that I'm doing. It's this really amazing instrument that it has this huge field of view. So it's an imaging camera that that can just image large regions of the sky at a time. And it's really great for doing these things called surveys, which are basically large campaigns or programs to image large regions of the sky. You can just go and just tile everything really quickly. And so the work that I'm doing specifically with it is I'm leading a program with a new imaging filter they've put on the instrument that's very sensitive to the metal contents of stars. And what this basically is a proxy for is kind of like how ancient the star is. So with this imaging filter on that camera, we are leading an effort to image a large fraction of the southern hemisphere with it, so about a quarter of the southern hemisphere, to really map out the distribution of ancient stars in the sky in that region of the Milky Way. And by doing this, we can do a pretty comprehensive investigation of the ancient stellar populations of our galaxy. We can cross match this information to the motions of stars that we have, and really, perform a comprehensive analysis of it's called chemodynamics. It's the chemistry and the dynamics of stars to understand the early Milky Way, the dwarf galaxies in that region of the sky, and kind of how this all fits together to give us an understanding of early galaxy formation and stars.
So, what do you guys hope to find? Is there anything you are predicting to find or be shocked about when you guys are looking into the dark energy camera?
Yeah, yeah. So one thing that I'm really excited about personally is this filter will be able to identify stars that formed at the very beginning of the universe. One thing that I mentioned was that stars are interesting because their outer layers preserve the chemistry from when they were formed. So what we're expecting is to find a large number of these stars that formed in the early universe through this imaging filter. Like, we will depict them out pretty quickly. And we'll be able to do detailed studies to understand what their chemical composition is, and then understand what the chemical composition of the very early universe was in a lot of detail. So, you can do that. You can get like the composition of 18 elements by doing this. With JWST, you can get, maybe 5 or 6, I think. So you get a much more detailed picture of what the chemistry of the early universe might have been like. And a decent number of these stars, by decent number, I mean about 100, we expect to find about 50 to 100 stars that were directly enriched by the very first stars themselves. So the first stars lit up in the universe and then exploded and spewed out elements. And then the second generation of stars formed enriched by those elements. And so by finding these second generation stars, you can understand what elements the very first stars in the universe were producing and what the nature of the very first stars might have been. And the first stars are an interesting frontier in astronomy research because they really began transforming the universe into what we see it as today. And we expect to find, like I said, 50 to 100 of these and really map out what elements, abundant space, what the properties of these early stars might have been like. The program has been going on for about a year now, and we've already found a few, and excited to see what more we'll find.
Definitely. But I also had a question. But why do you think it's so important for us to understand the first elements that created, these galaxies, these stars? Why do we need to know more about them?
Yeah, it's actually a really good question, and a very good philosophical question, too. So I think it's kind of an inherently interesting question, right? To map out the history of the universe from the very first stars to what exists today. Um, and so just qualitatively figuring out what elements formed first in the universe is a very key part of that story. It actually sets interesting things about the physics of subsequent generations of stars as well, or the subsequent generations of stars. Um, from a from a more astrophysical perspective, the nature and properties of the first stars is actually really interesting because it sets pretty fundamental parameters in how galaxies formed and in how the distribution of ionized gas and things like this in the early universe might have looked like. And so when people generate models of galaxy formation and galaxy evolution and they want to understand the physics of it, having an understanding of what the conditions of the very first stars might have been like, how this will affect their models, how this affects observations, is a pretty important part about pushing our understanding of physics in different regimes. Um, so, from a qualitative perspective, it's interesting to be like, this is the story of the universe. But from a more physics perspective, it's interesting because these objects really set the initial stages of how galaxies form and evolve. And that influences physical models that we use to investigate these things and learn more about physics and learn more about, what star formation in the early universe might have looked like. I don't know if that answers your question, but I'm happy to
Yeah,
talk
definitely.
more if needed.
All part of a learning process, and I think it's also the same as asking why do we need to know the history of our history, like humanity's history? Why is it so important? Because I think that in understanding what had happened in the past will help us model out how what'll happen in the near future. So I think it's very important. So our last section, which as we're coming to the end, is a little bit about you, about your journey in astronomy. How did you come about entering astrophysics? What inspired you? And just a brief little bit about that.
Yeah, so I've always been interested in space. So I really enjoyed going to planetariums when I was younger. I enjoyed watching documentaries on Kiwi. I read A Brief History of Time when I was in eighth grade. I thought all of these things were really interesting. But I think a lot of people actually find this interesting, and it's very difficult to make that transition from, interesting to this is what I'm going to do, right? And I think from that perspective, I was very lucky in when I went to undergrad, I declared a physics major. I wasn't quite sure what area of physics I wanted to do. I did a few different research projects. And I had a very good undergraduate research mentor in astronomy. And I had a very good undergraduate research project experience as well. So I was investigating how, um, like, kind of like explosions in the center of our galaxy, identifying these, trying to see what those might have been. And it was a very exciting project. And then so from undergraduate, after working on that, I got into PhD programs. And then I made the transition there to studying um, galactic archaeology, galaxy evolution, because I always thought it was interesting to study how things formed in the universe as well. So it seemed like an interesting area. And so that's kind of how I made the transition from what I did in undergraduate to my PhD to what I do now. But the journey was at a very high level. I was always interested in this, but I didn't think I would end up doing it as a career. And I was very fortunate in having good research projects that, showed me what research was like in astronomy, and that kind of set me on this path.
That's great. I think talking to such, inspiring astrophysicists like yourself is kind of motivating me to also go into the field of galaxies, the formation of our universe, the chemical evolution, and so forth. And I also wanted to know, some advice that you may have for, young astronomers like me or people who are just as interested in astronomy and just want to start out, how they can start out, and your opinion on that.
Yeah, I think reading is very helpful. Reading more, talking with people, having some sort of contact with people who are working on this. It can be difficult. I mean, especially if you don't have access. But, I think it's always helpful to to be able to get advice from someone who has gone through the process. And whether that be through listening to a podcast online or, contacting people at a local university or just having these discussions, it can be very, very helpful. Um, and I think once you enter undergraduate, if you're still interested in pursuing this kind of field, it's very important, again, to have a community of people or find a community of people who are also interested in this, get advice from them, and find some mentors in the faculty who are either able to help you with research or help you navigate the process. It's always much easier than doing things alone, is what I've found. And it's always a good thing to ask questions, ask lots of questions.
And I think I'm very, very motivated for astronomy. Obviously, my interest might change, but right now I'm very, very strong in astrophysics. And I think that's amazing advice that you should always reach out to, people who are already in the field, and you can gain more insight to, is this what I really want to do when I grow up? But thank you very much, Anirudh, for today's session. I learned a lot about dwarf galaxies, much more about the dark matter involved in them, the dark matter halo, which I didn't know much about, and especially galactic archaeology, which I'm definitely going to be looking more into. So thank you very much for joining us. I hope you can join us again. But I hope to see you very, very soon. Thank you for joining us at Astro Podcast.
Thank you very much again.